Hi all, welcome back to Computer Organization course. We'll get started. We will start the discussion from indexing and arrays or the indexing mode. So what happens here is the effective address of the operand is generated by adding a constant value to the contents of register. So in the last class we had discussed about the effective address, right? So what is the effective address? The instruction does not give the operand or its address directly. Whenever there is an instruction, it does not give, suppose it does not give the operand or its address directly. Instead, what it does, it provides the information from which memory address or the register the operand can be determined. This is called as effective address. Now in index mode, the effective address of the operand is generated by adding a constant value. This is important, adding a constant value to the contents of the register. Now, like this is a constant and the constant can be added to the content of register. We have to note here that this register can be a special register or it can be any general purpose register like R0, R1, R2 like this. Okay. Now, this register what we use in the index mode, it is called as index register. Maybe this could be this ri, this could be a special register or it can also be a general purpose register like r1, r2, r0. So in both the cases this register we call it as index register. And how do we symbolically write index mode? Like this, x of ri, that means x is a constant here. The constant has to be added to the contents of the register, and whatever the address we get, it will give the address of the operand. Now it can be written as, that is, effective address is equal to x plus ri. That is, the bracket here represents the contents of ri. Okay. Effective address is calculated by adding a constant to the content of the register. Now we should note here one more point, that content of the register is not changed. The register we call it as index register, and even after generating the effective address, the content of the register is not changed. Okay. Now we will see the two ways to represent this addressing mode, that is index addressing mode. The one way is your offset is given as a constant. So consider this example. These two are two different ways. Okay. These two are two different ways. First we will check this one. So if you have an instruction add 20 in bracket r1 comma r2. Now what does this specify? This is an offset, and this offset is given as a constant here. So first the content of r1, we will check the content of r1. What is present in r1? 1000 is present. Now what is 1000? It is a memory location. Where this memory location is present? It is here, right? Now what you have to do? You have to add 20 to this location. So how much is the answer? 1000 plus 20, you have 1020. Again, this 1020 is a memory location and it is present here. So what you have to do now? You have to check, you have to take or read the operand from this location or the data from this location. Then what happens? Once you have read the data from this one, you have to add it with the R2. Okay. Getting it how this works? First, you have to check the content of R1. 1000 is present, 1000 is a memory location. You have to add 20 to this memory location. You will get 1020, which is another memory location. Then, from this 1020, you have to fetch the operand and then add it with R2. This is one way of representing a index mode. The second way is where we present offset as an in the index register. So if we consider the instruction add 1000 in bracket we have r1 comma r2. Now here 1000 represents the memory location which is present here. The offset is present in the register r1. This content of r1. What is the content of r1? It is 20. Now this 20 will be added to this location 1000. How much you will get? 1020. Again this is a memory location. The content of this memory location 1020 is read out and then it is added with the R2. Getting it? So these are the two ways to represent the index mode. We will now consider a simple example having a list of test scores for the students taking a given course. Okay, so this is a diagram for that. So this is a memory wherein you have n number of students, n could be 5, 10 or whatever, how many. Okay, so n could be the number of students. Then you have the student details present like the student ID, marks for test 1, marks for test 2, marks for test 3. Then the next student, his marks for test 1, 2 and 3. Now say suppose the number of students it is stored in a location n and this is the first front of the your list. Okay, then you have list again, this is a memory location name. So here the first student id is present. This id can be roll number or your register number so that a student can be identified. Okay, then the next the test 1 marks for this particular student is present in list plus 4. Now this is a memory location list plus 4. So why it is list plus 4 and then it is again list plus 8? Why every time the 4 it's an increment of 4? That is because the assumption here is the memory is byte addressable and the word length is of 32 bits. Okay. Now we should note that in this figure it represents a two-dimensional array having a single row and 4 columns. That means so it is like a single row having 4 columns, something like this. Okay, a row having 4 columns wherein the first column has student ID, then the second column has test 1 marks, the third one has test 2 marks and the fourth one has test 3 marks, something like this. Okay, suppose now we want to compute or we want to find out the sum of the scores obtained on each of the test and store these three sums in some variable. Then how can we do? That means suppose I want to say we have two students. Okay, here student 1 and student id is the right. We consider there are two students and we want to compute the marks obtained in test 1 with the marks obtained by the student 2 in test 1. Like this we want to compute the marks. Then how can we do that? So a possible program is given here. R0 acts as a index register. Now before the loop is entered, the R0 is set to point to the location of the first student record. That means this student. Okay, then it contains, okay, as per this your R0 right now contains the value list. Okay, here hash list R0, this is that right. So what does your R0 contains? Your R0 contains the value list by default whenever this is executed. Now clear R1, R2 and R3. So these three registered by default or in the first iteration it is cleared to 0. Now, why are these clear to 0? We want to calculate the sum of three particular courses, three tests, and we want to store it in the location sum 1, sum 2, and sum 3. So, this register might contain some values, right? So, it is always better to clear this register and then use them. Next, we have the instruction move n comma r4. Now, here n denotes the number of students. Suppose if we consider there are two students are present, then your r4 what it contains? It contains 2. So this is an assumption. Okay, n is our assumption, that is two students are present. Next, we have an instruction add 4 in the bracket R0 comma R1. Now what does this mean? So this is an index mode, right? We got to know this is an index mode. So first, what is the content of R0? We will check. The content of R0 is list. This is a memory location. So what you have to do? You have to add 4 to this one. So what happens? Here R0 is list plus 4. This is your new memory location. Take the content from that and add it to R1. Okay, so first what happens? It goes to list plus 4 location and then its content is added with R1. Getting it? If you see this diagram here, list plus 4 is the right. first student's test 1 marks is taken and then it is added with the register R1. So what is the content of register R1 right now? Suppose it is 0 and say suppose your list list plus 4, it contains a value 2. Suppose this contains a value 2, this contains value 3 and this is 5. These are marks. Okay, now this is the student 1 and here is student 2. Again he has got the marks 5, 5 and 5 in each subject. Okay, so by default what happens, if you consider this one, add 4 of R0 comma R1. Now 4 of R0 is what? It is list plus 4. So what is list plus 4 here? It is test 1 marks of student 1. So the value here is 2. Now this 2 is added with what? R1. What is the content of R1? 0. So now R1, what does it contain? It contains the value this 2 plus 0. So it is 2. Then the next instruction, add 8 of R0 comma 2. So R0, what was the content of R0 here? List. So list plus 8, take the content from that and add it to R2. List plus 8 is what? 3. 3 you added with what? 0. So your R2, what it contains? 3 plus 0 is 3. Then you have add 12 of R0 comma R3. So what is the content of R0? List. List plus 12. You go to that location, take the content and move it to R3. So what is the content here? 5. 5 plus what is the content of R3? 0. So what is your R3 value right now? It is 5. Getting it? Now this is the marks of the first student. Now add hash 16 comma R0. R0 is our list. Okay. So add plus 16 to this one. So where do you go? You come here. List plus 16. What does it contain? It contains the roll number or the ID of the second student. Next, what you have to do? You have to decrement R4. What by default was, what was your R4? It was 2. Now what is the content of R4 here? It is, you have decremented, right? 2 minus 1. It means it is 1. Then you have to check branch greater than 0 loop. What is branch value here? It is R4. Is R4 greater than 0? Yes, right? Because 1 is greater than 0. Where you have to go now? You have to go back to this add instruction again where your loop is present, right? You have to go back here. Now it contains add 4, 4 of R0 comma R1. So what was the content of R0? If you say list, it is wrong because we have added 16 to this list. So what is R0 contain in the first iteration? It is list plus 16. Your R0 is currently at this location. Then what you have to do? You have to add 4 and then to the content of R1. So 4 of R0 list plus 16. Then you have to add 4, that becomes list plus 20, right? 16 plus 4 is 20. So what is the content of list plus 20? So you have added 4. Right now you are here, right? This is list plus 20. Then this is list plus 24. Then this is 28, right? Now what is the content of list plus 20? It is 5. Take that 5 and add with the content of R1. What was the content of R1 before? It is 2. 5 plus 2 how much? So R1 value is 7, right? Then add 8 to the content of R0. Then add it with the R2. What was the content of R0? It was list plus 16. Now add 8 to it. 16 plus 8 how much? 24. List plus 24. What is the value? You have 5 again here. Take that 5 and add it to the content of R2. What was R2 previously? It was 3. So R2 is 5 plus 3, that is 8. Then add 12 to R0. That means list of 16 plus 12. How much? List plus 28. What is the content of it? Again 5. Add that 5 to the content of R3. That is 5. 5 plus 5, it is 10. So R3 contains the value 10. Now what you have to do? Add 16 to R0 again. What was your 16? Previously what was the content of R0? It was list plus 28. Sorry, it was list plus 16, right? So the new value of R0 is list plus 32. That means 16 plus 16, it is 32. Then what you have to do? Decrement R4. What is the value of R4 previously? It was 1. 1 minus 1. That is R4 is now 0. Right? So then what you have? Check if R4 is greater than 0. Is 0 greater than 0? No, it is false. Then what happens? This instruction is executed. So what you have to do? Move R1 comma sum1. This means move the content of R1 to sum1. What is the content of R1? 7, right? 7 will be moved to memory location sum1. Then move R2 comma sum2. This means the value 8 will be moved to sum2. Then move R3 comma sum3. This means value 10 would be moved to sum3 memory location. Getting it? Next we will see about the relative addressing mode. Now what happens here is the effective address, it is calculated by the index mode. Same like your index mode, the effective address is calculated. But instead of your index register, right, instead of that register, what you use here is a program counter. Okay, instead of the, how do you calculate effective address in the relative mode? So instead of the general purpose register, okay, you use program counter and add the offset, right? Now when this can be useful, when this relative addressing can be useful, it is used to access the data operands, but the common use is in the conditional branch instructions. Okay, so what happens? Suppose if we take this example, branch greater than 0 loop. So what happens here is, so this loop, okay, it can be as we see here, this loop, right? You have a branch condition here and the loop is here. It can be backward or it can be forward. So the offset has to be added accordingly. Okay, how this location is calculated then? The location is computed by specifying the offset from the current value of the program counter. Since, as we had already discussed, the loop may be either before or after the branch instruction, this offset has to be a signed number, either plus or minus. Okay. Next, we will see the additional modes such as auto increment mode and auto decrement mode. So in the auto increment mode, how do we calculate the effective address? Let's see. Okay. The effective address of the operand is the content of the register specified in the instruction. Now what has to be done is, first the content of the operand has to be accessed, that is fetched. Then the register would be automatically incremented to point to the next item. Remember, in auto increment mode, the content has to be first fetched from the register, then automatically it would point to the next item. Okay, now how do we represent that? We represent something this, like this. Into the bracket, we have some register, then plus sign here. This means it represents the auto increment mode. It means the content of the register are first fetched, then it is incremented. Now here the increment value is 1. Every time when we have this auto increment mode, by default it would be plus 1. Okay. But in a byte addressable memory, this mode, what it would do is it would access successive bytes. Getting it? Next we have auto decrement mode. So in auto decrement mode, the reverse of the auto increment mode is done. What does that mean? So here in the decrement mode, the contents of the register specified in the instruction are first automatically decremented and then they are used as a effective address of the operand. So how do we write that? So we write something like this. First minus, then into the bracket we have some register. Okay. So here is a program in which we have the auto increment mode. So in the indirect mode we had seen this program, but here instead of that, instead of two add instructions, we can do it in a single instruction by using the auto increment mode. So what it does, first we will move the content of n to a register r1, then this is immediate addressing mode, right, hash num1 comma r2. Then what do? We clear the register R0. Next, we will add the content of R2 to R0 first, then R2 would be incremented. Okay. So likewise, we can calculate the sum of n numbers here. Next, there is a quiz. So the instruction add 20 of R1, 20 into bracket R1 comma R0. It represents which addressing mode? And your time starts now. That's it for today. We'll conclude our session. Thank you.